Okay, so hello everyone. In this particular lecture, we are going to discuss about feed-forward neural network. Okay, but before that, we should understand what is this neural network is. What is this neuron is, right? Now here are two images. So this particular image is of biological neuron. This is biological neuron. Okay, and this is basically a artificial neuron. Artificial neuron. So we are not going into a biological part of this particular neuron, but we should know how both are analogous to each other, right? So this is dendrites here you can see. So these all are the dendrites, okay? And this will act as a input to this particular neuron, okay? And this is basically a nucleus. This is basically a nucleus, or we can say a node, and this will act as a activation function, right? Activation part. So if you talk about this particular biological neuron, how it works, so there are dendrites. So dendrites will take input from various sensors we have, right? It will give that input to this particular nucleus of this particular cell body. Okay, it will activate that particular nucleus or node, and it will give the output. So this axon is basically a output. So this will be a output, right? And these are the different output terminals. Okay, and these are the different output terminals. Also, we can call it as synapse in biological terms. Synapse. Synapse. Yes. So this is how biological neuron is. But how it is analogous to artificial neuron? See here. So this is basically a function, right? So in engineering, there is one basic diagram we used to draw. So there is input, there is some process, and there is some output, right? There is some output. It's input, process, and output, and feedback is also there, right? So this basic thing we have learned in our first year of engineering, because if you observe, everything, each and everything has this particular architecture. There is input, there is some process, there is some output. That's it. Right? Same thing is here also. So this is basically a neuron. You can say our artificial neuron. Okay, how it is in and how it is working. So this will work as dendrites. So this will work as dendrites. We are just comparing both biological and artificial neuron, right? And there is some bias. So every neuron has some bias. So this is basically a bias. And here you can see there are two functions, right? So first one is pre-activation function, and this is called as activation function, right? Activation function. And this is the output of this particular neuron, and these are the output terminals, right? These are the output terminals, and this will be act as input for a next neuron, okay? Because we are dealing with the neural network here. So this will act as the input for a next neurons. I hope you understand the analogy between biological neuron and artificial neuron, okay? So but how this artificial neuron is working, that we can discuss it now, okay? So now let us consider one neuron first. So neuron has two parts, right? And we have different input like this. If you observe, we have different input. For example, x1, x2, x3, and we have some bias also. Okay, bias indicated as b, for example b, and we generally refer it as x naught equals to 1. Okay, this is basically a bias. So this will act as an input to this particular neuron, and we have the output also. Output, right? And here we have two things. First thing we already discussed, that is basically a pre-activation function. But what is actually pre-activation function? That is basically a scalar linear combination. Okay. So this x1, x2, x3, these all are the vectors. Okay. These are the vectors. So this x1, x2, x3, these all are the vectors. And when we give input to this particular neuron, so this is what pre-activation function will do. It will convert this basically into a scalar linear combination. So how does it work? So basically here what will happen, it is basically a xi into wi plus this particular bias. What is xi? This particular dendrites, or we can say input x1, x2, x3. What is wi? Wi is basically respective weight, okay, weight of each input. This w3 for example. So if we consider only three input, that is x1, x2, x3, so what this activation function will do? So how this pre-activation function works? Pre-activation function works. It is basically a summation of xi wi plus b I varies from 1 to n. And for this particular example, this will be like this: x1 w1 plus x2 w2 plus x3 w3 plus b, right? So we are converting this particular input of a vectors to a scalar linear combination by using this particular function, right? In the next part, and the input of this and the output of this particular function is given to the next part. And this is basically activation function, right? This is basically activation function. And this is basically a non-linear function, right? And this is basically a non-linear function. So left side part is basically a scalar linear combination, that is a linear function, and this is basically a non-linear function. Okay, please remember this point. The input of this particular scalar linear combination is given to this particular part. Okay, so in short, how we can represent in simple terms? So this, consider two things are here. So this will act as summation, this will act as f. These are the different input to this particular pre-activation function. The output is given to f, and f is basically a non-linear function. F is basically a non-linear, because in the real world the data is non-linear only, and then the output of this particular function will be considered as the activation function. Activation function. Okay. Please remember this important point. But I hope you understand this left side part. Okay, so left side part is clear to everyone, because what we are doing here, we are simply taking the input having particular weightage respect to vectors and some bias is there. So what this scalar linear function will do, it simply convert this into this particular form. So summation of each vectors into the weight of this particular vectors plus this particular bias. Okay, so this is what the scalar linear combination will do. That is basically pre-activation function, and the output of this particular function is given to this non-linear function. So this non-linear function, and here you can see non-linear function. So if you observe, we have three different non-linear functions. Okay, we have different non-linear function. We can use any non-linear function in this case, but we will discuss generally three types of non-linear function. But before that, let's denote this pre-activation function as z. Okay, so z equals to this one, right? So here z equals to summation of xi into wi plus b. Okay, so this is what z will do. Z equals to summation of xi wi plus b. Okay, so this is basically my scalar linear combination. Okay, now the input of this particular scalar linear combination is given to a non-linear function. So what is non-linear function here? So here we have three non-linear function. First one is sigmoid. So we already discussed the sigmoid function in our logistic regression. Okay, logistic regression. Okay, and second one is that tan h. So hyperbolic h, hyperbolic tan function. Then third one is that rectified LU, that is rectified LU, that is re-LU, right? So these three functions are mostly used in the case of this particular non-linear function. There is one more thing, that is basically softmax. Okay, so we'll not going to discuss, but you can explore it. But these three are important for exam point of view. Okay, so I already provided the notes for this particular topic. You can just go through it. In that also I have mentioned these three non-linear function, but I will show you how this particular non-linear function works. But before that, I hope this working of neural network is clear to everyone. So simple, we have input. So input is basically dendrites in the terms of biological neuron having particular weightage. So that input with along that weightage and bias is taken by this particular pre-activation function, that is basically a z equals to summation of xi wi plus b, and the output of this particular thing, so this will act as a z. So z is given out input to the non-linear function, and the output of this non-linear function will be an activation function. Okay, so this is how this particular neuron works. Okay, so this is how this particular artificial neuron works. Okay, artificial neuron works. Okay, so I hope this structure is clear to everyone. Now we'll discuss about what is non-linear function in this case. So first we'll simply discuss with by example of sigmoid function. All right, sigmoid function. So we have discussed the sigmoid function in the logistic regression part. It is given as sigma of z 1 upon plus e to the power minus z, right? So this is basically a sigmoid function, right? And if you observe, this Z is basically a output of pre-activation function. Pre-activation function, right? So if you compare this here, so what I can write, Z is basically this one, right? So I can say if I use this sigmoid function as non-linear function, then it will be equivalent to like this, 1 upon 1 plus e to the power minus summation of xi wi plus b, right? So it will be like this, right? So output of this particular function is basically my activation function, and this is denoted by a, okay, and this is denoted by a. So this is basically activation function, okay. The output of this particular function is taken as an input for other neurons, okay. So this is the basic structure of artificial neuron. So this is about the sigmoid function, okay. Now if we talk about other two functions, so this is the graph of sigmoid function and tanh function, right? So we already discussed this, because if you observe at x equals to 0, means at z equals to 0, this particular value is 0.2, right? And this is the graph of the sigmoid function, and the value of this particular sigmoid function is between 0 to 1. And if you compare with the tanh function here, right? So this is a tanh function basically, and the output of this particular tanh function lies between -1 to 1, okay. And here it is rectified ELU. So this particular graph for rectified ELU. So if you observe, whenever my z is greater than 0, then it is linear, okay. When it is linear, you can see this graph. But when it is less than 0, it is 0, right? This is what rectified ELU is. Now what is leaky RELU? So leaky RELU is having some components to it. So whenever my x or z is greater than 0, that is basically a linear function, right? That is basically z only. But whenever it is less than 0, it is basically AZ, right? So value of A can be anything less than 1, right? That is basically a AZ, right? It can be less than 1 or greater than 1 also, but it depends. So that is basically a leaky RELU. So I hope you understand this sigmoid function, tanh function, and RELU function, right? So no need to go in detail. Just remember this particular graph and a formula. You can just remember. So this thing very important, okay. I have not included in the notes. I have just put the theoretical concept in the notes, but this thing also you can remember for exam point of view, okay. And this sigmoid functions and this, okay. So this is particular graph of sigmoid activation function and tanh activation function, right? Now if you observe, for a higher value of z or x, so I will consider this as z, for example, z. This is basically a z, and this is also z, right? Z. So for a higher value of z, in both the cases, if you observe, the saturation points are there. Here, if you observe, here, if you observe, right? Here, here. So if you take the derivative of the sigmoid function and tanh activation function, here you can see it is close to 0 only, right? It is close to 0 only in both the cases, right? It means that our neural network will work slow, will work slow. It will process the data slowly if we use this both sigmoid function or tanh function, because for higher value of z or lower value of z, it is close to 0 only. And if you observe, the derivative of this particular tanh function is more than sigmoid function at z equals to 0, right? And here also you can see the range of this particular sigmoid function is 0 to 1, and tanh function is -1 to 0. So generally, tanh function is preferred over the sigmoid function. So this is the basic of non-linear function, right? The output of which is given to a next neuron. Okay. I hope you understand this non-linear function. Nothing in it. Just look at this particular graph, understand it. Okay. And whatever I have explained, if you understand, that will be enough. And go through the notes. That is enough, right? So we have discussed about the non-linear function. So this complete will act as a one neuron. Okay. Now what is neural network? We have discussed about neuron. Now what is neural network? So this thing like everyone knows. So we have different neurons here like this. Then this is basically act as an input layer. So this is basically input layer, and this is basically a output layer. And here we have some hidden layer. So this is basically a hidden layer, right? So this all are called as hidden layer. Hidden layer. So each neuron will take a different input here. Here you can see different input. Okay, so this will act as an input to a neural network, right? It will process this particular input and the non-linear output is given to a next neuron here. Here you can see this one like this, right? Here also it will give like this. So this will form a neural network, okay? So this is the input. The non-linear output of this particular neuron is given to this particular next layer, that is hidden layer. Okay. So in this way, this particular neuron will work. Neural network will work. Okay. Simple. I am not going to explain this, but I hope you understand how this neural network is formed. So this is basically input. So this is basically input layer or called as zeroth layer. This is Lth layer, and this all are basically L minus one layer. Okay. So this is basically hidden layer. So this is basically simple neuron network. So input is given and the output is also, and output is will be like this, right? Okay, so like if I want to represent, so this is basically a neural network. It is feed-forward neural network. So this is basically layer 0, input layer. Layer 3 is basically output layer, and these two are the hidden layers. So hidden layer 1 and hidden layer 2. Here you can see. So this So input layer is considered as x1, x2, x3, right? So output of this particular neuron is given as an input to a next neuron. That is basically next layer. So in this way, this particular neural network will work. And this is simple architecture of a neural network. And here you can see flow of information. So flow of information will go in this particular direction. That is feed forward a neural network. So how this feed forward neural network works? So it consists of input layers. So this layer consists of neurons that receives input. So how this particular new input layer works? So this layer consists of neurons that receive input and pass them on the next layer. Here you can see the next layer, right? The number of neurons in the input layer is determined by the dimensions of input layer. Okay, remember this point: dimensions of input data. Okay, and this too will work as a hidden layer. Okay, hidden layer. So what this layer will do? So this layer are not exposed to any input or output of particular directly of this particular layer. So this hidden layer will take the input from the input layer, right? And this hidden layer will take the input from the hidden layer 1. So in this way, the flow of information works in the feed-forward neural network. Okay, so each hidden layers neuron take the weightage sum of the output from the previous layers, right? And apply an activate function to it, and then pass the result to the next layer. So this is about the neural network, right? And this is basically a prediction. So output layer is basically a prediction, right? So we are using this network, a neural network for prediction only, right? So I hope you understand the architecture of this feed-forward neural network. Nothing in it, just flow of information is there. It went from the input layer, so it will go from input layer to the output layer in this particular path. Okay. So for the rest of the thing, you can just refer to the notes, so that will be enough. Okay. So working of feed-forward neural network involves two phases. So first one is feed-forward phase, and other one is back propagation phase. So what is this? Basically, back propagation phase. So what happens in the case of feed-forward phase? In this phase, the input data is fed into the network, and it propagates forward to the network. At each hidden layer, the weighted sum of the input is calculated and passed to an activation function, which introduce non-linearity into the model. Right. So this is what we have discussed in the previous slides, right? So this process continues until the output layer is reached and prediction is made. And how this back propagation works? Once the prediction is made, the error, that is basically difference between predicted output and the actual output, is calculated, and this error is then propagated back to the network, and weight are adjusted to minimize this error. So if you observe this particular network, right? So this will have this input, for example, x1, x2 like this, right? And here having some weight w1, w2. So how we are calculating this weight w1 and w2? So basically we have to iterate this particular weight. Okay, so in short, we need to find out w1, w2 and bias value only to train this particular neural network, right? So how to optimize this particular parameter? By using back propagation phase, right? So this will be an error. So this error is then propagated back to a network and the weights are adjusted to minimize this error, right? So same thing, whatever I have discussed previously in the slide, in the first slide, right? So input is there, output is there, then we have this feedback, right? And some process will be going on. So same system is there, okay, in the neural network as well. Okay, the process of adjusting weight is typically done using the gradient descent optimization algorithm. So there are different optimization technique in this particular topic. So we can discuss that, but it is not required for gate exam point of view. But just remember the name, that will be enough. So what are those optimization techniques? So first one is gradient descent. We all know what is this. So it's an iterative optimization algorithm that adjusts weight and biases to minimize the loss function. Okay. What about learning rate? It is a hyperparameter that determines the step size in the weight and bias updates. Okay. So based on this particular technique, there can be a numerical as well. Okay, numerical based on this particular learning rate. So they can ask simple numerical based on this learning rate, because we can solve such type of numerical, simple numerical within a minute. So you can expect a numerical based on this learning rate. And then next optimization technique is basically a mini batch gradient descent, right? So an optimization technique that process the training data in small batches to speed up the convergence. So these three optimization technique generally follow in the neural network. Okay, I hope you understand what is neuron, what is nonlinear function, what is sigmoid, tanh, rectified, ALU, basically linear unit, right? And why this working will be slow if we use both sigmoid and tanh function, right? So the drawback of this particular function, right, sigmoid and tanh function can be overcome by using ReLU function, right? So that's it from this particular video. Okay, I already provided notes for this, so kindly go through the notes, so that will be enough. Okay, thank you.